misnomer to begin with. Not a misnomer, but not a descriptive term. And therefore, it misleads a lot of people into thinking things that aren't really, at least misled me for 20 years. Huh?
So you're talking officially now?
I'm just talking officially now.
Sorry, he's talking officially.
Yeah. So, yeah, because this is too much screwing around.
Yeah.
I can make the basic point, and you're going to want to read the paper anyway, and at least I always do. I get nothing out of a 15-minute presentation except a bunch of buzzwords that tickle my curiosity. The non-locality is a non-descriptive. It's a non-descriptive term. It doesn't evoke the right idea immediately. Let's rename it. Let's call it electromagnetic causality.
You're on the screen.
What? It's up there now.
Yeah, it's just a slow computer.
Oh,
Now it disappears.
there's a tremendous time lag, because that's what was here before I did some other things.
No, it's over there, but on your computer.
There's a fire across it.
Well, there is a switch
No,
that you
no,
can use
when
to
you-
go on both.
And
You've
this thing is
lost
not
the rest of the
misbehaving.
screen now.
No, I can carry on.
Now, what if you do?
You've got a bad
Carry on
connection
talking
somewhere.
now. Don't bother. If that comes up, so be it. Well, let's carry on talking.
What? Just talk, just talk.
Just talk.
Everyone else
Yeah,
is quiet.
yeah, right, it's not, anyway, the term non-locality doesn't evoke the right thoughts. Didn't for me. I was a sucker for the story for 20 years. The whole time sensing that something is seriously wrong, either with my understanding or with the presentation of the story. After working on it a while, I've come to the conclusion, if it had been named electromagnetic causality in the first place, right at the beginning, then I wouldn't have spent 20 years, maybe 10 years, but not 20 years, worrying about it. So it's been a campaign of mine, personal issue kind of thing, to figure out exactly what does it mean and how did it come about. Search the literature, what you'll find is that there are quite a large number of papers. I have a stack about 3 inches thick of papers in which people propose classical phenomena that have exactly the same structure as the experiments that are credited with proving that quantum mechanics has some non-locality involved somehow. Given that those models were in the literature, a number of people have tried to simulate the experiments point by point by point by point. It turns out that those simulations have all been unsatisfactory one way or another, although they're getting better and better. I have several of them for different experiments. At a certain level, it's easy to do the simulation, it's easy to get the answer, it's easy to correlate the phenomena with classical phenomena. What's difficult, however, is to correlate it with classical phenomena as the experiments are done, where you just read one point at a time. The issue turns out to be that what you need, the information you need to do the calculation from the data in the experiment is an intensity reading. However, when you're doing it at what's called the 1 photon level, you don't have an intensity reading. You have a yes or no. You got a click or you didn't get a click. If you want the intensity information, you then have to repeat that particular measurement and then take the ratio of the number of times it appeared in your data over the size of the data sample space. And that gives you a relative intensity in terms of the frequency that that particular type of signal generates. Now, when you do the experiment, you have to do two things. You have to get a data point, but then you have to repeat that data point often enough to extract the intensity from it. Somehow or another, when you do the experiment without knowing what you're doing, it works out. However, the theory of the experiment requires the use of the singlet state. The singlet state, as we all know, is a sum of two mutually exclusive possibilities. Namely, it's polarized this way or that way, or it's polarized, or it's up and down at the same time. And of course, that's a logical abomination. So naturally, one would like to think there is some way to interpret the singlet state so that it makes sense, and on that basis, do a simulation. And I worked on that for a long, long time. And I thought, well, what the singlet state really is not a state, but a representation for many states, at least two. And so the singlet state was a statement which should be a probabilistic representation for either or. Either it's left or it's right. Either it's polarized vertically or it's polarized horizontally. And consider in doing that mode, that gets damn close. And it gives you the right correlation, but it's this logical abomination, once again, that bothered me. So, going back and looking at the literature and all the examples that people have, you see that they're not using the singlet state. What they're really using is a uniform bias, a distribution of uniform biases. They're saying that the two signals that are generated in these experiments are anti-correlated, but are random in terms of the total polarization. The polarization, brother, in each case rotates around on the whole sphere, not rotates around, it jumps around on the whole sphere, such that you get a more or less uniform distribution for the whole sample. So the goal then becomes to figure out how to program that all into a simulation. Now, two other points I'd like to digress here and jump off to the side and say, well, what's really happening here historically? Well, historically is that, of course, Bell proposed something he calls a derivation of an inequality. If you examine that in great detail and with great attention, what you discover is that he has a key equation in his story, and I can write that down very quickly. And that is that the correlation of that's over all the lambdas. The correlation, let me back up once more. What is he trying to do? Based on the observation that quantum mechanics is a probabilistic theory, and a weird probabilistic theory, however, he says, perhaps it's weird because there's a bigger theory, a higher theory, as it were, although it could be a lower theory, which has additional variables that are such that when you integrate over these variables and project the bigger theory back down to quantum mechanics, makes quantum mechanics sort of an average of that, is weird. But it's not weird in its full glory. So he then hypothesizes how things should be in this transcendental or meta theory, how they should be perfect in that theory. They should follow all the rules of ordinary probability and physics and have no non-locality and none of this other stuff. No collapse of the wave packet or anything. Should be a normal, regular classical theory. Might maybe relativistic or some other thing. So then he asked, what constraints does that put on projecting the correlation coefficient from the higher theory where you have the lambdas? And then he writes, well, if we have the lambdas up in the higher theory with pertaining to the Alice and Bob of both sides of the experiment, and we average over all of the lambdas, then we should get the correlation function computed in quantum mechanics. So he's saying at the higher meta level, we should have an absolute probability for what Alice sees times an absolute probability for what Bob sees, integrated over all of these things. But this formula is not a normal probability theory. Is not a normal probability formula. He's assuming that what happens on each side is correlated. And if it's correlated, then you can't write it as the product of two absolute probabilities, you have to write it as the probability of a product of a conditional probability times an absolute probability. This is a conditional. Now, all of that so far is really just notation. But a conditional probability is a different beast than an absolute probability. And what happens is, if you put a conditional probability up here, the derivation of the inequalities comes to a halt. You can't do it. In order to derive the inequalities, you have to factor these things and so on and so forth, and remultiply. None of that factoring goes through unless the A and the B are symmetric in structure. They can pertain to different things, but they have to look more or less the same, and they have to behave the same. But they don't. They don't look the same, they don't behave the same, because this is a conditional probability. That says if you want to compute this product, you look first for B, and whenever you see a B, then you look to see if there's an A. If you don't find a B, you don't even bother looking for the A, because you're looking for the correlation. And the only time this degenerates to that is when they're non-correlated. So he put, but he did so symbolically with this formula. If you derive it with this formula, then it's correct only when they're non-correlated. So that's one story. That guarantees that there's something a little bit wrong with the Bell inequalities. They don't mean what we think they mean. Not backing up and stepping aside and going to another arena, you might note that the experiments are done in qubit space. That has to do with polarization and so on. Qubit space is structured so that it's governed, so to speak, by the group SU2. That group is homeomorphic to S3. S3 is a group of rotations on a sphere. The non-commutivity of S3 has nothing to do with quantum mechanics. It has something to do with geometry. If SU2 is homeomorphic to it, then the non-commutivity of SU2, which is the space of spin and all this kind of stuff, has nothing, can have nothing to do with quantum mechanics either. The non-commutivity will turn out to be, again, due to geometry. Therefore, the whole venue where we're doing the experiments, where the experiments are done these days, namely in quantum optics with polarization of the different signals, is in a venue where from the start there's no quantum mechanics. There's no quantum mechanical structure. So one obviously can't do experiments in that venue to plumb the structure of quantum mechanics, be it non-locality or whatever, in a venue where there isn't any. So once again, it guaranteed that there has to be some means of simulating these experiments classically. The question is, why have so many of these attempts at simulating the actual experiment, the way it's done, the way the data is taken home, not been really satisfactory? And I've come to the conclusion that the reason for that is, once again, this problem with determining what the intensity is, because you have to use the intensity classically in the formula for correlation. So you've got to repeat this thing in a certain cycle and get that intensity up. And in fact, I've written such a program. It's not as elegant as it ought to be, and as I hope it will become, but it does it gives approximate answers, of course, which is also what happens in the experiments. They never quite get a perfect answer, no matter how much data they analyze. And that's because the sample, it turns out the sample has to be of this roll, has to be uniform, totally uniform, in a finite stochastic sample will never be completely uniform. There'll always be some bumps. So the final conclusion of my presentation really is that, first of all, Bell's theorem is erroneous. It doesn't apply where you really want it to apply. And secondly, the space in which the experiments are being done, so to speak, this SU2 structure, is non-quantum from the start, so it won't work. 3, there are many classical models that have the same mathematical structure and give you the same correlation, in which when you plug into the Bell inequality should indicate, if the Bell inequality were correct, that classical physics is also non-local, which I think we know is not the case. Certainly there's no evidence for it. And finally, if somebody wants to do a simulation, point-by-point simulation that mimics all aspects of the experiment, including generating the data, taking the data, analyzing the data, you've got to be clever enough to somehow or another find a way of extracting the intensities of the signal as they're needed for computing the correlation using classical correlation functions. So that was the guts of my story. Had I had a working projector here, you would have seen the pictures of the equations that are involved and perhaps recognize some from previous calculations you've done one way or another. But the conceptual point is still the same. There's no proof for the existence of non-locality in quantum mechanics. So thanks for your attention.
Are you saying because I can make the relationship between SU2 and S3 on which is classical,
Yeah?
then I'm interpreting the SU2 group in a classical sense because of that mapping, that homeomorphicity. Is that what you're saying?
I'm saying that I'm projecting onto other people, have interpreted the quantum character of spin space as being, I've interpreted spin space as having a fundamental quantum character because of its structure and the structure of its non-commutivity. I don't think I'm unique in that. I think I learned that right out of the textbooks.
But the SU3 is always used as a spin space for quantum mechanics.
It is used in quantum mechanics. Many things fit into quantum mechanics that are not essentially quantum mechanics. The question then is really, where is quantum mechanics?
That's what I'm trying to get at. In other words, in the SU2 and SU3 scheme, it seems to fit very well with the quantum mechanical picture. But if I make it homeomorphic to a classical space like S3, does that imply that even SU3 is somehow?
That's rotations on a sphere. We know that has nothing to do with. We know that has nothing to do with quantum mechanics.
Why does it
SU2
really seem to work out to explain the particle physics and symmetry breaking?
Well, if that part works out and does explain it, then it's doing so without quantum mechanics. Quantum mechanics is there where Hamiltonian conjugate variables do not commute because of Heisenberg uncertainty.
Right.
Okay, where are those places? There's two,
Uh-huh.
phase space
Right.
and squeeze space. Squeeze space is for waves, huh? It's
Right.
phase and amplitude. Phase and amplitude pertain to the direction of a wave parallel to its wave vector, huh? Mm-hmm. So imagine my finger to be a wave vector. Perpendicular to the wave vector, we have two vectors that characterize polarization.
Right.
Okay? Now, when you change the wave vector around, S3 it, as you were,
Right.
give it a S3 treatment, it wiggles around, right? What happens to these guys? They go with it.
Right.
That's the plane that goes with it. This is the wave vector, this is SU2, this is SU3, SU2. Neither of them are quantum mechanical. And SU2, after all, was worked out when first? Well, I don't know when first, but I know most famously about 1850-something or other by Stokes.
Yeah, way before quantum mechanics.
Way before quantum
I realize
Yeah.
it's used in the quantum picture,
Uh-huh.
so I'm a little bit,
Yeah. Well, the fact is, there's a lot of structure that we have. For example, vector spaces. You can do vector spaces by writing A's, bold A's with arrows over some, or you can use bras and kets.
right.
Now, a lot of people, if they see a vector in bra and ket, they think, oh, that's essentially quantum. It's not. It's just a vector. If it has a
That's
vector
right.
quality, it's a vector. It's a vector like any other vector.
Okay.
Garden variety vector.
So what you're saying is I could use my SU3, which came before quantum mechanics. And all I'm really doing is saying I either add H bar or I don't.
H bar in that case turns out to be just a scale factor for whatever it is. When you pick a vector, K vector, it has a length. And in the case of SU2, that H bar it corresponds to the length. It's not part of the wiggle structure, so to speak. It only characterizes it's the player's name, but it's not critical for the structure. It's not critical for the dialogue of the player or the action of the player or the dance or whatever the player's doing.
Okay.
It's just it's exasperating, I know, because it's everybody. I went along with this story for 30 years, and I was uncomfortable with it all the whole time. And I kept thinking this has got to be wrong, and I couldn't find the wrong, and
bothered about the prior causality on the light cone.
Yeah.
That.
Well, that's part of the story. See,
bothers me.
that was.
And I'm not sure how to interpret that, because it looks space-like in the now space, but it looks, time-like in the now and space-like in the past causality.
Actually, in quantum mechanics, probability doesn't care where the prior information comes from or how it got. Probability lives perfectly happily with non-locality. It isn't probability that's the problem. It's the idea that in quantum mechanics, a vector like the singlet state is a real thing, and that when you measure it, you never see it, of course. When you measure it, you see one or the other.
Yes.
Okay, so they couldn't figure this out, so what von Neumann, I think, suggested, right? When you measure it, it collapses, destroys one or the other, and so you only see one.
Right. Because
So it's the collapse that's non-local. When you do the Alice and Bob thing, you measure over for Alice, say, then you know what Bob has instantly. But that's the old trick, you take two gloves, put them in a box,
Yeah.
send one off to Sydney and the other off to London, then you tell them on Christmas Day at 9 o'clock, open the boxes and see what you got. When you open the box, you know exactly what happened at the other end. You know exactly which glove you got. But that's not causal. There's nothing causal about that. That's explained by prior.
Well, it's a prior cause of
Prior cause.
choosing to send the two gloves.
Yeah. Everything is
two
decided in the
different-
background.
Yeah.
Same way with Bob
Backwards
and-
light cone
The same way in these experiments, everything is decided at the generation of the signals. And then it just propagates out, and you measure it then. But nothing happens. Even you would never think that anything happened if it weren't for the projection hypothesis. The projection hypothesis is what makes everything weird. And the projection hypothesis, after all, is not even part of quantum mechanics. It's not part of Schrödinger equation. No solution of Schrödinger equation says you're going to get projection. That's something pulled out of the air to save the story. To reconcile the problem of having a vector that's supposed to have up and down in it, but you only see up or you only see down. So von Neumann said, well, evidently when you look, but that's not, there's no way, there's nothing you can put in your Hamiltonian to get a projection process going. It's a dictate from, a Curia kind of thing, huh? Like from Rome.
Yeah. Yeah, we had.
Yes?
Yeah, what does it mean for special relativity? Because this
Well-
experiment was connected to that. How do
No,
you
it's
understand
only
that?
connected with special relativity in the sense that this projection process is supposedly transferring something from one point to another instantaneously, and not
A signal.
respecting the speed of light.
Yes. sometimes-
That's the only. It has absolutely nothing to do with special relativity, except that it constitutes supposedly an example of something weird and wonderful happening in quantum mechanics that special relativity can't explain.
Well, it's a space-time issue.
So,
Yeah.
And so that makes you think of special
Yeah.
relativity.
Right.
are you saying something like special relativity is valid, but quantum mechanics
Yeah.
isn't?
Am I saying anything like that?
Yeah.
No.
No. Okay.
I'm saying that both of them are useful tools
Yeah.
if you don't make the mistake of applying them where they don't apply.
Okay.
But we might not know where they apply and don't apply. That complicates the story.
I was thinking last night when we talked,
Yeah.
okay, so if there's a Big Bang cosmology, we'll call that a prior cause. So then what would be correlated between one galaxy and another? Which
Yeah, well,
would
that
be
gets
sort
into
of
the
like
issue
Alice
of
and Bob.
free will. Is there any free will, and where does free will come from and all that? And a lot of people have tried to argue philosophically that free will comes from this collapse process. It's the collapse that introduces some monkey shines in the whole thing, that offer that break the solid links that everything would have if
but
you
in a
believe in a
certain
Descartes-type classical mechanics.
Yeah, this prior cause says that there's a limited amount of free will, which seems to make sense to me.
Uh-huh. Yeah, well, if there is free will, or the free will issue, I think, will be solved, not from quantum mechanics, but probably from chaos theory, where you have spontaneous, what do they call, bifurcations.
Yeah, right.
That's the only window I see at the moment, and that might not be a window,
Yeah, but what
really.
determines the bifurcation?
Yeah.
Is it the agent that has the free will, or is it a deterministic backlog?
It only pertains in those cases where this bifurcation is spontaneous or unaccounted for by the structure of whatever's bifurcating.
Right, okay.
And so, that's, again, puffy, blah, 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 because I don't know that there's suitable bifurcation theory at all, but I see there's a glimmer of a hope there, rather than in mechanics. Any other questions, comments, brickbats, whatever?
Yeah, let's give Alan another hand.